So let's consider a vector field, A, in Cartesian coordinates with components x, I hat, plus y, j hat, plus z, k hat. All right, so we have that at x equals 2, then this vector field has 2 in the component in the say horizontal direction if x is to the right. Same thing for y and for z. We could draw this this vector field. So right at the origin, this vector field, x equals 0, y equals 0, z equals 0, it's 0. So there's no there's no arrow to draw there. But let's say we move. Let's move along the x direction, which say is to the right. Right. So for x equals say 1, this is 1, and for y is 0, z equals 0. We just have an x component, and so it looks like that. And as we move further this way, it gets larger and larger, and so we would have something like this. Right? And the same thing would be true for the y direction, if that's the y direction, and outward for the z direction. So we can draw some of these. And to the left, it would be negative, but it would be the same kind of thing. It would look something like that, getting larger and larger. In the negative y direction, like that. And then, of course, we could have x and y components and have z equals 0. So an x and a y, positive x and y would produce a vector field that looks like that. 1 is negative y and 1 is positive x. It would look like this. Both negative, we would be down here. And negative x and positive y would give us something like that. Okay, so that's what the vector field looks like. And we want the curl of this vector field. Does this field have a non-zero curl? Well, we know that the curl is the derivative of the z component of the vector field with respect to y, right? The y component with respect to z, and that is the x component of the result. The y component involves the derivative of the x component with respect to z minus the z component with respect to x. And the z component of this vector field involves the y with respect to x and the x with respect to y. And so we can immediately see that this will give 0 because the x component only has an x value, and the y component only has y, and z only has z. And so when we take derivatives of a component with respect to some other variable, as we have to evaluate the curl, we're going to get 0 for all of these components. So this is a curlless vector field. In a sense, A does not change as you circle or curl around. We could ask whether A diverges. It looks like A is diverging, so A diverges, right? So an electric field wouldn't be like this because it wouldn't be growing, but A diverges, so we can say divergence of A is not 0 everywhere. Let's say we have a vector field that is different from this one. It looks like that. There's a constant value in the z direction. The z component is always constant. So if we have an x this way and a y this way and a z outward, sorry, let's do x, y outward and z upward, then our vector field would look like this. Everywhere it would have a length of 3. Right, so look, this everywhere, and if we move more in the positive y direction, we're moving upwards this way, but we always have vector fields everywhere, arrows everywhere of length 3 pointing in the same direction. So let's do the same calculation, right? The curl of A involves this kind of thing, but our component, our only component, is a constant, so it doesn't vary. And therefore, this also has to be 0. So this is a curlless vector field as well. It also happens that this field is divergenceless as well. The divergence of this vector field is also equal to 0. So we're starting to get a sense of what kinds of fields don't have a curl, and the ones that have a divergence or not. We'll want to get to vector fields that do have a curl.